All right. Welcome to Unit 3. We've been building up to this point all semester, and we're going to take what we know about describing data sets that we learned in Unit 1 and kind of describing the differences between different data sets like we learned in Unit 1. And we're going to combine that with what we know about probabilities now, which we learned in Unit 2, in order to make inferences, right? In order to look at data sets and say, yeah, we can be, such and such amount sure that this result is true in the general wider population. So that's kind of what the whole moral of the story is in Unit 3. One of the main tools that we use to perform inference is hypothesis testing. So in the next two sections, we're going to talk about one sample hypothesis testing. In this section, we will just talk about hypothesis testing kind of generally and introduce some of the reasoning and some of the language that we use when we're doing hypothesis testing. And then we will also talk specifically about a hypothesis test, a one sample hypothesis test for the proportion. In the next section, we'll talk about a one sample hypothesis test for the mean. So let's get to it. Just to kind of introduce the idea, let's consider a few scenarios. So this first one says, a random sample of 300 children were given Medco's new antibiotic, and 2.3% of them experienced a headache after taking the medication. A researcher for the Food and Drug Administration wishes to know if we can conclude that more than 2% of children taking this new antibiotic experience headache as a side effect. Now, the question is there enough of a difference here to say that the new antibiotic causes headaches more than 2% of the time? Now, where did this 2% come from? We don't really know. It could be that 2% is the headache rate among competing antibiotics that are already available on the market. And so if this new antibiotic causes headaches a greater percentage of the time, then maybe the FDA would be hesitant to, want to recommend that drug. So that could be the case here. We don't really know fully what the situation is, but we just want to know whether there's enough evidence to say that this new antibiotic causes headaches more than 2% of the time. And at first glance, it might seem like, well, yeah, 2.3% is more than 2%, but it's not that much more. And this 2.3%, it could just be due to sampling error, right? It could just be that just by random chance, you happened to get a sample of people who responded poorly to the drug, or maybe they just got headaches even though it wasn't related to the antibiotic at all. So is 2.3% enough? Is it different enough from 2% for us to say for sure that this antibiotic causes headaches more than 2% of the time? That's a question that we're going to learn how to answer, at least partially, in this section. But for now, I think you can see, that's kind of a difficult question to answer right away. Number two, is similar kind of a thing. It says, according to QSR magazine, Chick-fil-A fills their drive-thru orders with 96.4% accuracy. A curious fast food fanatic wonders if the accuracy is lower at her local Chick-fil-A, so she collects information from the store manager about the drive-thru accuracy of the local Chick-fil-A. In 350 orders, it was found that 93% of the orders were accurate. Is there a large enough difference to say that the local Chick-fil-A is less accurate? It certainly seems that way at first glance, right? 93% is less than 96.4%. This time there's more of a difference than there was on the first example, right? But still, it's only like a 3.4% difference. Is that a big enough difference? Maybe not. It could just be due to random chance. So how do we know, right? How do we know? Maybe on this particular day where there were 350 orders, they just had an off day or something. So it's hard to say, And then a third example, a recent poll found that 83% of people say they like unicorn giggles. A tired parent believes that percentage would decrease if people were first required to watch an episode of My Little Pony before saying whether they like unicorn giggles. 150 participants were randomly selected and made to watch an episode of this show. 77.3% of patients reported liking unicorn giggles. Is there enough of a difference here to say that watching My Little Pony makes people less enthusiastic about unicorn giggles? Okay, well, so there we have, like a 5.7% difference. I think I did that math right. You should double check me. But I think that's like a 5.7% difference. So that's a larger difference even than number 2. So now maybe we're getting somewhere. Although, notice this, that on number 2, we had a sample size of 350. As our sample sizes grow, the likelihood that we are observing the results that we observed just by random chance shrink, right? The more evidence we have, the better the evidence is. So on number 2, we had 350 people and a 3.4% difference. On number 3, we have a larger difference, but fewer people in the study. And so, again, it sort of begs the question, well, is this good enough evidence? Like, do we have good enough evidence to say or to substantiate our claim? And so the whole reason that I'm giving you these examples right off the bat is to just point out, like, man, wouldn't it be nice if there were a mathematically rigorous way to decide when we have sufficient evidence to support our claims? And that's exactly what hypothesis testing is all about. So the way we judge whether evidence is mathematically compelling is called hypothesis testing. In hypothesis testing, we observe whether the data that have been collected are adequately explained by the null hypothesis, or if the null hypothesis must be rejected in favor of the alternative hypothesis presented by the researcher. So in hypothesis testing, the null hypothesis, which is denoted with an H sub 0, is, you can think of it like the status quo. It's what we assume to be true until we have evidence to suggest otherwise. The null hypothesis is going to be a statement that a population parameter is equal to some claimed value. And that value will usually be given to us within the context of the problem we're looking at. But the null hypothesis is a statement of no change, no difference, no effect, etc. So, we'll look at some examples where we'll write out some null and alternative hypotheses in a second. But that's the null hypothesis. The alternative hypothesis is usually the statement that the researcher is trying to find evidence to support. And the alternative hypothesis will denote with an H sub A. Sometimes it's denoted with an H sub 1. But HA is a statement that the value of a parameter is different than what the null hypothesis says. It's a statement that indicates change, difference, effect, etc. Hypothesis tests, specifically the alternative hypothesis, can be two-tailed, left-tailed, or right-tailed. In a two-tailed test, the alternative, well, first of all, notice that in all 3 tests, the null hypothesis is always that the parameter equals some value, right? It's always an equals, right? The null hypothesis is a statement of equality. In a two-tailed test, the alternative is that the parameter does not equal that value, as stated in the null hypothesis. In a left-tailed test, it's that the parameter is less than the value. And in a right-tailed test, it's that the parameter is greater than some value. So let's practice seeing if we can write down some null and alternative hypotheses, and then we'll state whether the test that we've just written out is a two-tailed, left-tailed, or right-tailed test. As we're doing so, we're going to do kind of some mixed practice here. And I think the 2 main parameters that we'll be testing are going to be proportions and means. And when you're trying to decide, well, which how do I tell when I'm testing a proportion and when I'm testing a mean, I think that a dead giveaway is to look at the kind of data that you're working with. If it's categorical data, then you'll most likely be testing a proportion. Whereas if it's numerical data, then you'll most likely be testing a mean. So let's practice. Part A says, the Medco pharmaceutical company has just developed a new antibiotic for children. 2% of children taking competing antibiotics experience headaches as a side effect. A researcher for the Food and Drug Administration wishes to know if the percentage of children taking the new antibiotic who experience headaches as a side effect is more than 2%. Okay, so to decide whether we're testing a mean or a proportion, we should ask ourselves, Well, what kind of data do we have here? If you ask people, or if you have a group of children who's been a part of this study, whether or not they have experienced a headache as a side effect of taking this antibiotic, their answers are going to be yes or no, right? They're going to say, yes, I got a headache, or no, I didn't get a headache. That's not numerical data, right? That's categorical data. And so we're most likely going to be testing a proportion. You can also see that the question that we're being asked is if the percentage of children who experience headaches is more than 2%. Well, a percentage is the same thing as a proportion, right? It's just that a proportion is expressed as a decimal, but otherwise they're the same. So we're definitely testing proportions here. The null hypothesis, of course, is that, no, this antibiotic is the same as the other ones, right? No change, no difference, right? The null hypothesis is that the proportion of children who experience headaches as a side effect is 2%, right? The same as every other antibiotic. The alternative hypothesis should be the claim that the researcher is trying to show, right? The researcher for the FDA wants to know if the percentage is more than 2%. So we want to know if P is greater than 0.02. So that's how the null and alternative hypotheses would look on part A. This is a right-tailed test, okay? Because the inequality is pointing to the right. So this is right-tailed. Part B. The Blue Book value of a 3-year-old Chevy Corvette Z06 is $56,130. Grant wonders if the mean price of a used 3-year-old Chevy Corvette Z06 in the Miami metropolitan area is different from $56,130. Okay, so there we're kind of given a dead giveaway. Grant's wondering about the mean, so we're going to be testing means. But besides that, we're talking about the price, which is a numerical variable, so we would be testing the mean. We want to know if, on average, the price of these Chevy Corvettes is different from $56,130. Now, the null hypothesis would be that it is not, right? That it's the same price, right? That mu equals $56,130. The alternative doesn't say anything specifically about whether the mean is smaller than that or bigger than that. It just is asking if the mean is different from that. So the alternative hypothesis is going to be that mu does not equal $56,130. And that makes this a two-tailed test. Okay, a couple more. Please pause the video and see if you can get the null and alternative hypotheses written as we go through these examples, right? So part C says, suppose that 83% of people say they like unicorn giggles, but you think that that percentage would decrease if they were subjected to an episode of My Little Pony. So go ahead and pause the video, see if you can write down the null and alternative hypotheses here. Here's my answer. We're testing proportions here, right? We want to know if fewer than 83% of people will say that they like unicorn giggles after watching an episode of this show, right? The null hypothesis is that, no, the show is not going to have any effect. It's still going to be 83% of people saying that they like unicorn giggles. And the alternative is that it's going to be smaller than that. The show is going to annoy them, and so they're going to be less likely to say they like unicorn giggles. This is a left-tailed test. Okay, last one. An agricultural chemical company believes that they have developed a fertilizer that causes corn stalks to grow taller. They test this fertilizer on 100 corn stalks, that should just say on 100 corn stalks of a certain variety that usually grow to be 2.7 meters tall on average. Okay, so the corn stalks usually grow to be 2.7 meters. The null hypothesis is that going to be that this fertilizer doesn't have an effect, right? No effect. So the null hypothesis is that the average height, mu, is 2.7 even with the fertilizer because it has no effect. The alternative is that the fertilizer works, that it causes the corn stalks to grow taller. So in which case mu would be greater than 2.7 meters, and that makes this a right-tailed test. Okay, so that's how we would set up null and alternative hypotheses for one sample hypothesis testing. Once we have our hypotheses set up, we weigh the evidence to decide whether or not to reject the null hypothesis. But then the question is, how do we come to our conclusion? And for that, we'll look at an example. So to kind of get us thinking about how we would arrive at our decision, let's consider this scenario. And this scenario is going to be posted as a discussion board prompt. So if you haven't participated in this week's discussion board, pause the video now and go participate on the discussion board. But here's the scenario. So suppose you're taking a biology class that studies animal behavior and you're assigned the following topic to research. Okay, so the topic is this. In a certain species, mallards, male ducks have green heads and females are a plain color. Probably the purpose of the green coloring of the male heads is to attract the females. The question is, are female ducks also attracted to the green color in food, for example, in bread? So the first task here, if this were a face-to-face class, I would let the class kind of talk to each other about how what experiment you might come up with to test this. But that's kind of what the discussion board will be about. Just so that we're all on the same page, I've gone ahead and written out an experiment that we could use. So we might decide to throw a piece of plain colored bread and a piece of green colored bread simultaneously at a duck, and then record which type of bread the duck approaches first. And then we repeat the experiment maybe 30 times or so. Okay, so that would be an experiment that we could perform and start to collect data on. Now let's write out the null and alternative hypotheses. The null hypothesis is that the proportion of times, the null hypothesis basically is that the duck has no preference, right? There's no difference in the way the duck approaches the green colored bread versus the plain colored bread. If that's the case, then the proportion of times that the duck approaches the green colored bread first is going to be 50%, right? They're going to approach the green colored bread 50% of the time and the plain colored bread 50% of the time. So the null hypothesis is going to be P equals 50%, right? Where P, and maybe we should say where P is the proportion of times the duck goes for the green first. Okay, so if there's no difference in the duck's preference, then they're going to go for the green 50% of the time, right? Half the time. If, on the other hand, the duck prefers green bread, then they're going to go for green more than 50% of the time, right? P will be greater than 50%. Okay, now if female ducks were truly indifferent between green and plain bread, about how many ducks would you have expected to choose the green bread first? And well, we're going to repeat the experiment 30 times. If half of them go for the green bread first, then we'd expect 15 of them, right? We would expect n times p, right? 30 times 0.50, which is 15, to go for green first. Okay. Now, suppose that you find that 65% of female ducks sampled prefer the green bread. So then the null hypothesis states that the proportion P is 50%. 50%. But our sample proportion is 65%, which is quite a bit more than 50%. Let me try again. 65%. So yeah, that's quite a bit more than 50%. If female ducks are really indifferent to plain bread versus green bread, which is what we're saying here, what is the probability that 65% would pick the green bread first just by random chance? Because it is possible, right? It is possible that we're getting 65%, even though ducks really don't have a preference, but it's just by random chance that just happens to be the case, that in our sample, 65% of them went for the green bread first. But what's the probability of that happening, right? What is the probability that 65% would pick the green bread first just by random chance? And would this give us good evidence that female ducks are attracted to green bread? Well, let's see. We are looking for the probability that we would get a sample proportion of at least 65%. Well, we talked in the last chapter about how to compute probabilities involving the sample proportion. What we said is that the sample proportion follows a normal distribution. So we're going to use the normal distribution in Desmos to calculate this probability. It follows a normal distribution with a mean of mu sub p hat, of course. Mu sub p hat is the same thing as p, right? This was all from section 2.9, right? The sampling distribution of the sample proportion. And p, well, we're assuming that p is 50% from the null hypothesis. Okay? So p hat is normally distributed with a mean of 0.5 and a standard deviation of sigma sub p hat, which is the square root of pq over n. That's the square root of 0.5 times 0.5 divided by our sample size n. We said that we would repeat 30 times. Okay, so let's see. Square root of 0.5 times 0.5 divided by 30. So that's about 0.09, although we could just use the exact value, which I might do. Okay, so we're going to use the normal dist with a mean of 0.5 and a standard deviation of square root of 0.5 times 0.5 divided by 30. We want the probability that p hat is more than 0.65, so our minimum is going to be 0.65. And we're not going to have a maximum, we'll just put infinity, and then we can find this probability. So let's see what we get. So normal dist with a mean of 0.5 and a standard deviation of square root of 0.5 times 0.5 divided by 30. Let's zoom in on that. Find the cumulative probability. We want the probability that p hat is greater than 0.65. Okay, so that comes out to 0.0502. Okay, so there's our probability. The question is, would this give us good evidence that female ducks are attracted to green bread? Well, in the past, we would say anything that has less than a 5% chance of occurring is unusual. And in this case, we did not get a probability of less than 5%. So we wouldn't necessarily call this unusual, although we're going to update our understanding surrounding that issue in a second. But for now, just using the same cutoff that we've been using in the past, we would say, no, this isn't super unusual. it's possible then that this could just happen by random chance. And therefore, this is not super great evidence, and so we should not reject the null hypothesis. In other words, we calculated this probability here by assuming that p was really 50%. And we didn't get a super small value, and therefore we can't assume that there's anything wrong with the null hypothesis. We shouldn't reject our assumption. So we could say since 0.0502 is greater than 0.05, we would not consider this result unusual. Therefore, there is not good enough evidence. We should not reject the null. Okay, so that's kind of the idea of hypothesis testing. In fact, this probability that we just computed, this one right here, is what's known as the p-value. The probability that we computed in the duck scenario was an example of a p-value. To compute a p-value, we compute the probability of obtaining the results in our study, assuming that the null hypothesis is true. And now this is somewhat counterintuitive, okay, but the idea is that if the resulting p-value is small, then that gives us reason to suspect that our assumption was wrong. In other words, we compute the p-value assuming that the null hypothesis is true. If what we end up getting for our p-value is a really small number, then it tells us that maybe we were wrong to assume the null hypothesis, and so we reject it. So a small p-value leads to rejection of the null hypothesis. So the p-value of a hypothesis test is the probability that we would collect a random sample that yields the sample statistic that we obtained, or something more extreme than that, assuming that the null hypothesis is true. We're going to talk about how to find the p-value for testing a mean mu in the next section. For now, let's just practice finding p-values for testing the proportion. So number 2 here wants us to state the hypotheses and compute the p-values for the following scenarios. We've already stated, I think, the hypotheses, but we can still find the p-values. Part A says, a random sample of 300 children were given Medco's new antibiotic, and 7 of them experienced a headache after taking the medication. A researcher for the Food and Drug Administration wishes to know if we can conclude that more than 2% of children taking this new antibiotic experience headache as a side effect. So the null hypothesis is no, right? That the proportion of children who will experience headache as a side effect is 2%, the same as it is for every other antibiotic. The alternative hypothesis is that p is greater than 2%, right? That's the claim that the researcher is trying to tackle, right? They want to know if the proportion is more than 2%. The sample evidence that we have, right, our sample proportion p hat, was that 7 out of 300 children experienced headache as a side effect. 7 out of 300 is about 0.023. Okay, so that's 2.3%, right? Which is in fact bigger than 2%. It's not that much bigger, but it is a little bit bigger. Is it enough of a difference? Well, to know that, we would need to compute the probability of obtaining something that large, right? What we want is the probability that p hat would be at least 2.3%, since that's what we observed in our sample. And we're going to use, of course, the normal calculator to compute this probability, right? So we'll go to the normal dist. We're going to use a mean, assuming that the null hypothesis is true, right? So we're going to use a mean of 0.02. And we're going to use a standard deviation of square root of 0.02. Let's see, if p is 0.02, then q is 0.98, right? 1 minus 0.02 is 0.98. And then we would divide by our sample size of 300. Okay, now since we want the probability p hat is more than 0.023, we're going to set our minimum at 0.023. And our maximum we'll set at infinity. So the p-value, right, is the probability that we would obtain the sample statistic that we obtained, or maybe something more extreme than that, okay, under the assumption that the null hypothesis is true. So that's what we're computing here. Let's see what we get. So still using the normal distribution, but I'm just going to change p to 0.02. 02. This would be 0.98, and 30 was 300. We had a sample size of 300. We want the probability that p hat is more than 7 out of 300. Okay, so it looks like there's about a 34% chance of that happening. 0.3400 if we round to 2 decimal places. So there's our p-value. So no, I would say we don't have super great evidence here, right? 34% chance. 2.3% is just not that much bigger than 2%. Okay, part B. It says, according to QSR magazine, Chick-fil-A fills their drive-through orders with 96.4% accuracy. A curious fast food fanatic wonders if the accuracy is lower at her local Chick-fil-A, so she collects information from the store manager about the drive-through accuracy of the local Chick-fil-A. In 350 orders, it was found that 326 of the orders were accurate. Okay, so this fast food fanatic wonders if the accuracy is lower at her Chick-fil-A. So the null hypothesis is that it's not lower, that it's the same as it is everywhere, right? The proportion of the accuracy rate is 0.964. Okay, and the alternative is that it's lower. The sample evidence that we have is that 326 of the 350 orders were filled accurately. 326 out of 350. .931-ish. Okay, so yeah, that is less than 96.4%. Let's see if that's statistically significant, right? So we'll say we want the probability of obtaining the sample result that we obtained, or something more extreme than that. Now, in this case, more extreme would be, since this is a left-tailed test, more extreme, if 0.913 is unusual, then anything smaller than that would also be unusual. And we're going to compute this probability under the assumption that the null hypothesis is true, that p is 0.964. So in that case, we know that p hat is going to follow a normal distribution with a mean of 0.964 and a standard deviation of 0.964 times 0.036. You should double check me. And then divided by a sample size of 350. Okay. For our minimum value, since we're looking for the probability that p hat is less than or equal to 0.913, there's not going to be a minimum value. We'll just use negative infinity. And for our maximum value, we'll use 0.931. Okay, let's see what we get. So same normal distribution, 0.964, 0.964, 0.036, and then we had a sample size of 350. And we were looking for the probability that x was between negative infinity and 0.931. So that comes out to, did I have all of that right? 0.931? Yes. Okay, so that comes out to 0.0005-ish if we round to 4 decimal places. So that's our p-value. This is our p-value. Now that one would be good evidence. We would reject the null hypothesis there and say that this local Chick-fil-A, they really need to step up their game because they're making the franchise look bad. Okay, part C. A recent poll found that 83% of people say they like unicorn giggles. A tired parent believes that percentage would decrease if people were first required to watch an episode of My Little Pony before saying whether they like unicorn giggles. 150 participants were randomly selected and made to watch an episode of the show. Afterward, 116 participants reported liking unicorn giggles. Okay. So, null hypothesis is that watching this show is going to have no effect whatsoever, right? 83% are still going to be enthusiastic about unicorn giggles. The alternative hypothesis is that no, their enthusiasm is going to wane a little bit. That less than 83% of people are going to be in favor of these things. And the sample evidence that we have is that 116 people of the 150 in our sample said that they liked unicorn giggles. Let's see, 116 out of 150. 116 out of 150 is 0.7733. All right, so that's about 0.773. So yeah, that's a bit of a difference. However, our sample size is smaller than the previous example, and so maybe the probability of this happening is not so small. We'll see. We want to compute the probability that our sample proportion would only be 77.3%. Okay, so this is what we're looking for. We're going to use the normal distribution because p hat is normally distributed. We're assuming that the null hypothesis is true until we have evidence to suggest otherwise. So we'll use a mean of 83%, and we'll use a standard deviation of 83%, square root of 0.83 times 0.17 divided by 150. Okay, no minimum value because we want the probability p hat's less than 77%. Our maximum value should be 0.773. And let's see, so our p-value is the probability that p hat is less than or equal to 0.773. Oh, what was it? 0.83. Okay. And our sample size was 150. Okay, 0.773. All right, looks like there's about a 3% chance of that happening, 0.0316. Okay, and there's our p-value. Okay, so that one is less than 0.05, so maybe for now we would say, yeah, that's good enough evidence. We would reject the null hypothesis. Yeah, it looks like people's enthusiasm for unicorn giggles decreases a little bit if they're forced to watch My Little Pony. Okay, so this is how we get p-values. The last kind of piece of the puzzle is the level of significance. In the past, we've always used 0.05 as our cutoff for what we would consider unusual. But in fact, we can use any cutoff we like, as long as we set that cutoff value before we actually run the experiment. That cutoff value that we decide on is called the level of significance. It's denoted by the Greek letter alpha. Common values for alpha are 0.01, 0.05, and 0.10. Alpha is basically chosen based on how severe the mistake would be if we decided to reject a true null hypothesis. And that's something that we're going to talk about in greater detail later. But the key takeaway is this. We compute our p-value, and if it's less than alpha, then we reject the null hypothesis. If it's greater than alpha, then we do not reject the null hypothesis. Okay, and here, instead of saying p-value greater than alpha, I'll oftentimes say p-value not less than alpha, just to emphasize the fact that if the p-value is less than alpha, then you do reject. If the p-value is not less than alpha, then you do not reject. Sometimes students wonder, well, what happens if the p-value equals alpha? That's a very unlikely scenario. The p-value is almost certainly not going to be dead on exactly equal to alpha. But if on the off chance that it was, then we would still reject the null hypothesis. Okay, so we can also reject H null if the p-value equals alpha. Now, another thing to note is that we're not talking about accepting the alternative or rejecting the alternative. We never talk about accepting the null. Our decision is always either to reject the null or to not reject the null. And here we kind of get into a little bit of semantics. You might think, well, what's the difference between saying I'm not going to reject the null and saying that I accept the null? But to answer that question, it might be helpful to think of this in terms of a criminal trial, okay? When a jury acquits a defendant, it doesn't mean that the defendant is innocent. It just means that there's not sufficient evidence to convict them, right? It could very well be that the defendant is guilty, but there just wasn't sufficient evidence to convict. And it's the same way in a hypothesis test. We use this terminology that we are not going to reject the null hypothesis, and that's not the same thing as saying the null hypothesis is true. It's just saying we don't have enough evidence to prove that it's false, okay? So with that in mind, let's make some decisions. Number 3 here says, should we reject H null for the scenarios in example 2 if we use a level of significance of alpha equals 0.05? What if we use alpha equals 0.01? Well, let's see. In the Medco example, the p-value that we got was 0.3400. So here, the p-value was 0.3400. And that's going to be bigger than alpha whether we use a 0.05 level of significance or a 0.01 level of significance, right? So notice that 0.3400 is not less than 0.05. So we do not reject the null. This is if we're using alpha equals 0.05. Okay. If, on the other hand, the researchers had decided that we wanted to use alpha equals 0.01, well, then our case is even worse, right? 0.3400 is definitely not less than 0.01. So again, we would not reject We would not reject the null hypothesis. Okay, part B, the Chick-fil-A example. In that example, our p-value was 0.0005. Okay, well, this is just the opposite of the Medco example, because in this case, our p-value is so small that it doesn't matter which level of significance we use, right? At the alpha equals 0.05 level of significance, excuse me, we would reject the null, right? Because 0.0005 is less than 0.05. So we reject. We reject H null. At the 0.01 level of significance, if the researchers had decided to use that, well, we would still reject the null hypothesis because 0.0005 is less than 0.01, so we still reject. Finally, for part C, this is the My Little Pony example, we used a p-value of 0.0316, or we calculated that as the p-value. P-value .0316. Did I get that? That's right. Okay. Well, if the p-value is 0.0316, then at the 0.05 level of significance, we would reject the null hypothesis because 0.0316 is less than 0.05. But if the researchers had decided to use a 0.01 level of significance, on the other hand, well, then we would not reject the null, right? Our evidence doesn't quite meet the threshold that we set for ourselves. 0.0316 is not less than 0.01. So we do not reject H null. So this is how we make our decisions, okay? We compare the p-value to the level of significance alpha. If the p-value is less than alpha, we reject the null. If it's not less than alpha, we do not reject the null. Okay, one last step when it comes to hypothesis testing. Once we've made our decision, then we usually like to write a conclusion. The decision is a statement about whether we should reject the null hypothesis, okay? Whereas the conclusion is a statement about what our decision means for the alternative hypothesis. So the conclusion should be stated as a complete sentence that addresses the original claim. And I would advise that the safest thing to do is to just follow a strict sort of script on this. This is not a creative writing class, so you don't have to get creative. Just use the same the same setup every time. Okay, so if our decision is that we should reject the null hypothesis, then our conclusion should say something like, there is sufficient evidence to indicate, and then you restate the alternative hypothesis, right? If, on the other hand, our decision is to not reject the null hypothesis, then our conclusion should say something like, there is not sufficient evidence to indicate that, and then restate the alternative hypothesis. So, for example, let's write a conclusion for the following scenarios. In the Medco example, using the 0.05 level of significance, I think our decision was do not reject the null, right? Do not reject the null. In the Medco example, the issue was that there was a new antibiotic, and the question was whether it caused headaches in more than 2% of children. And basically our answer to that question is, well, we don't have enough evidence to say that it is, right? And that's what we would say in conclusion. So the decision was do not reject the null. And so the conclusion is there's not sufficient evidence to support the alternative. Okay, so I'm just copying verbatim. There is not sufficient evidence to indicate that. And then now I need to restate the alternative hypothesis in words. That hypothesis was that more than 2% of children experienced headaches as a side effect. So I'm going to say there is not sufficient evidence to indicate that more than 2% of children who take this antibiotic experience headaches. As a side effect. We can do the same thing for the My Little Pony example. In the My Little Pony example, the p-value is 0.0316. At the 0.05 level of significance, we decided to reject the null hypothesis this time. So our decision was to reject the null. And so our conclusion should say something like, there is sufficient evidence to indicate that, and then we restate the alternative hypothesis, right? So there is sufficient evidence to indicate that, and then we restate the alternative hypothesis in words. The alternative hypothesis in this case is that people's enthusiasm for unicorn giggles would decrease, right? That fewer than, I think it was 80, what was it? Fewer than 83% of people would like unicorn giggles after watching this show, right? So there is sufficient evidence to indicate that viewing My Little Pony causes the proportion of people who say they like unicorn giggles Okay, there's evidence to indicate that viewing My Little Pony causes the proportion of people who say they like unicorn giggles to decrease. Okay, so we've seen all of the steps in the process now, right? To kind of summarize and put it all together, the idea is step 1, we're going to state our null and alternative hypotheses. Step 2 would be to gather some sample evidence, either p hat if we're going to be testing a proportion or x bar if we're going to be testing a mean. Then we will compute a p-value, which is the probability of obtaining the sample result that we obtained if we assume that the null hypothesis is true. Once we have our p-value, we can use it to make a decision about whether to reject the null hypothesis. If the p-value is less than alpha, we reject. If the p-value is not less than alpha, we do not reject. Okay? And then finally, we'll write a conclusion about what our decision means for the alternative hypothesis. If we reject the null, then there's evidence to support the alternative. If we do not reject the null, then there's not sufficient evidence to support the alternative. So what I'd like to do now is just give you a couple examples where we go through the entire process from beginning to end for a proportion anyway. And then in the next section, we'll look at several examples where we go through the entire process for a mean. And we'll actually do some mixed practice in that section as well with means and proportions. Okay, so number 5 here says, according to the Centers for Disease Control and Prevention, 19.6% of children aged 6 to 11 years are overweight. A school nurse thinks that the percentage of 6 to 11-year-olds who are overweight is higher in her school district. In a random sample of 65 6 to 11-year-olds in her school district, 19 of them are overweight. At the 0.05 level of significance, is there evidence to conclude that the percentage of 6 to 11-year-olds who are overweight is higher in her school district? Okay, well, let's see. We'll start off by stating the hypotheses. The null hypothesis is that the percentage is not higher in her school district. It's the same there as it is everywhere else, right? 19.6% of children are going to be overweight. The alternative is that she's correct, right? That the proportion of children who are overweight is higher in her school district. So those are our hypotheses. Next thing we want to do is look at the sample evidence. It looks like she went out and collected a sample of 65 students and found that 19 of them were overweight. So her sample proportion of overweight students is 19 out of 65, which we could give as a decimal. So that's 0.2923 or 0.292. So 0.292, so about 29.2%. That is quite a big difference, I would say. However, her sample size was fairly small. She only had 65 students in her sample. And so even though she's observing a large difference, it could be the case that she doesn't end up rejecting the null hypothesis here only because she doesn't have enough evidence, right? She didn't collect a big enough sample size, but we'll see. I could be wrong. Maybe the p-value here is quite small. The only way to know is to compute it. So to compute a probability about a sample proportion, we will use the normal distribution. Assuming that the null hypothesis is true, p would be 0.196. Okay, and then we would use, for the standard deviation in our normal distribution, we would use the square root of p times q, 0.804, and then divide by the square root of our sample size, n. Okay. The minimum value, let's see. We want the probability that p hat is at least 0.292. So our minimum would be 0.292, and our maximum would be infinity. So let's see. Our p-value is the probability that p hat is greater than 0.292. Let's see what we get. So 0.196, 0.196, 0.804. Our sample size was 65. And we want to see if this is, if p hat is greater than 0.292, or what's the probability that p hat is greater than 0.292. I'm going to put infinity for my upper bound. And let's zoom in on that. So it looks like there's a little over a 2.5% chance of this happening, 0.0256. Okay. Step 4 now is to use that p-value to make a decision. Well, 0.0256, we were supposed to use the 0.05 level of significance. 0.0256 is less than 0.05. So we reject H null. Okay, And finally, we can write a conclusion. The question was whether the percentage of 6 to 11-year-olds was higher, of overweight 6 to 11-year-olds, was higher in this nurse's school district. And basically what we're saying is, yeah, the evidence seems to indicate that, right? So we would say there is sufficient evidence to indicate that the proportion of overweight students is higher in this nurse's district. And that's what a hypothesis test would look like from beginning to end. Okay? So let's do one more. And you should really pause the video and try this one out before I give you my solution to this. See if you can go ahead and run this hypothesis test from beginning to end. But I'm going to go ahead and forge ahead and give you my solution. In 1994, 52% of parents of children in high school felt it was a serious problem that high school students were not being taught enough math and science. A recent survey found that 397 of 800 parents of children in high school felt this way. Are parents less likely to be concerned about the level of math and science education today than they were in 1994? Let's see. The null hypothesis is that they're not less likely, that they are equally likely to think that, their kids aren't being taught enough math and science, okay? The alternative is that they are less likely to be concerned about this. The sample evidence that we have to support the claim is that 397 out of 800 parents expressed concern. In our sample, let's see, 397 out of 800. Is about 49.6%. Okay, is about 49.6%. Okay. So we want to compute the p-value now, right? We want to know, well, if I assume that the proportion of parents who are concerned is the same today, that it's 52%, what's the probability that in my sample I would have gotten a sample proportion of 49.6%? Well, let's see. We'll do, we'll use the normal distribution for this. Assuming that the null hypothesis is true, the mean of that normal distribution is going to be 0.52, and the standard deviation is going to be square root of 0.52 times 0.48 divided by 800. Our sample size was 800 here. Now here there isn't much of a difference, a little over 2% difference. However, our sample size is so large that we might end up rejecting, or we might end up with a small p-value. We'll see. To compute the probability we want, we're looking for the probability that p hat is less than 0.496, so there's not going to be a minimum. The maximum is going to be 0.496, and our p-value is going to be the probability that p hat is less than or equal to 0.496. Let's see what we get. Sample size was 800, negative infinity, 496. Okay. So it looks like there's about an 8.7% chance of this happening. P-value 0.0871. Okay. So our decision. We are once again using the 0.05 level of significance. 0.0871 is not less than 0.05, so we do not reject H null. So we're saying that if we assume that the null hypothesis is true, there's still like almost a 9% chance of us observing this sample proportion, which means that it's not really all that unusual to observe this sample proportion under this assumption. And so we don't reject it, right? There's no reason to reject our assumption then, okay? So in conclusion, we would say there is not sufficient evidence to indicate that parents are less likely to be concerned about the level of math and science education. Okay, they're not less likely to be concerned about those things today, or at least we don't have sufficient evidence to say that they are. And this is despite the fact that we got a sample size of 800 parents, which is a pretty large sample size. So, yeah, I would say there's just not much there. Even if there was a difference, it's not a substantial difference, right? Okay. So that'll do it for this section. Again, in the next one, we'll talk about how to test means, and we'll do some mixed practice. But that's it for now.